So next week we have the mid-semester assessment. Just make sure that the lab session finishes probably about 10 minutes before the end time, so that you're on time here, so that you can start the assessment on time. So it'll be around 45 minutes worth of assessment. Probably about 50 minutes. Similar problems like this, I think I've uploaded a sample question as well, of questions. Probably 2 to 3 questions, I would say. Will be similar to the tutorial problems after the topics that we covered until week 3, as per my announcement on Canvas. And obviously it won't be the same questions repeated, but similar questions, right? So it wouldn't be an assessment if it's the same questions repeated. The way that I would see that if you are familiar with in solving all the problems that we solved today, in the tutorial problems, you should be able to get all the way to a credit, to a distinction. So if you were to get distinction to a high distinction, then that's the extra level of assessment that will be assessed pretty much. The difficulty level, it's not that high, but some conceptual and understanding of the topic is needed. As long as you understand what's happening in solving the problems, I don't think getting a distinction or a high distinction is that hard. It's not that. The difficulty level is not. Compared to the tutorial problems, it will be a bit different. I think it's a different type of questions. So, what else here? Just please be on time next week, and then make sure that you spread out and sit as well. We can start the assessment next week. Any questions on the assessment for next week? Yeah.
Actually, we have a lab session before this time.
The lab session before this? Yeah. So I was mentioning that it'll stop at 10 minutes before this time. So 4:20 or even 4:15. That's okay. You have enough time to take 2 lifts, right? Lift down and then lift up. Yeah. So that's I know the difficulty there. Okay. So this week, we're going to look at week 4 tutorial problems. This topic will not be covered in next week's assessment, so up to week 3 only. So, but this is an important topic that we need to cover. So the topic for this week is on again signal propagation. So we saw there are 3 classes of signal propagation: mean signal strength, large scale shadowing, and small scale fading. Right. So today we'll be looking at both large scale shadowing or shadow fading and small scale fading. And this problem is on small scale fading, and we'll have a look at it. So end of last week's session, we kind of went through some of the topics that we covered in small scale fading and large scale fading, and that's what we'll be today. So let's have a look at the problem first, and then let's go back and have a look at the slides for the relevant notes, and then we'll come back and solve this problem. So the mean signal to noise ratio measured in a Rayleigh fading wireless channel is given by 20 dB, the mean value. So why it's a mean value? Because a random fading channel. So we talk about statistical parameters for a random fading channel, like mean value of the signal to noise ratio. Calculate the outage probabilities for receiving 10 dB of SNR, 20 dB of SNR, 26 dB of SNR. Right. So the outage probability is the probability that signal strength falls below a prescribed level. So if you want a signal to noise ratio of, let's say, 10 dB, that's the expectation. When if the signal to noise ratio falls below that expected value, well, not the expected value as in mean value, but the prescribed value, 10 dB, then we say that the channel is in outage. So in this case, we want to calculate the probability in part A, the probability that the signal to noise ratio falls below 10 dB, and that probability is the answer for that. And in part B, the probability that SNR falls below 20 dB, and the probability that SNR falls below 26 dB. So this is our gamma 0. Gamma is 0 is the prescribed signal to noise ratio that we are targeting for the design. All right. So let's go back. Let's go to the lecture slides. So it says that we have start from the small scale fading. So we know for small scale fading, so this is lead 4 slides. For small scale fading, we have two main causes, multipath effect and relative motion between the transmitter and receiver, right? So we are now with multipath effect, we are looking at the multipath effect issues. And within multipath effect, so this is the multipath effect that we'll be observing, right? When a signal is transmitted, the first component is received at the receiver, and after a few delays, copies are received. Right? Now, the amplitude of these, the first arriving signal and the copies, the amplitude are modeled using a Rayleigh distribution. It's a random process. Right? So that's where this problem lies. So we have a multipath channel with a Rayleigh distribution, and so a Rayleigh distribution corresponds to non-line of sight scenario. So if you don't have a non-line of sight situation in the transmitter and receiver, there's blockages and so on. We model the amplitude of the multipath components with a Rayleigh distribution. If there's a line of sight, then we model it as a Ricean process. Right? So these are modeled using experimental measures, and then it seems to be a good fit. So a Rayleigh non-line of sight situation is when, for example, the transmitter is outside this room and the receiver is inside this room. So we don't have a line of sight between the transmitter and receiver. A Ricean process is when the transmitter and the receiver are in the same room, for example. Okay. So in the problem that we are addressing, we have a Rayleigh distributed channel. So we know it's a non-line of sight situation. That's the probability density function for a Rayleigh distribution, right? And that's how your signal amplitude or magnitude in the dB scale would look like. If you look at the, if you record the signal strength and square it up and then look at the dB of that, that's how the power would look like. And that's a non-line of sight scenario between the transmitter and the receiver. Okay. So in a Rayleigh distributed, in a Rayleigh channel, so we call that as a Rayleigh channel, right? The amplitudes are distributed using a Rayleigh random process, a Rayleigh distribution. Correspondingly, the signal to noise ratio, not the amplitude, the signal to noise ratio becomes an exponential distribution. Right? So the amplitude is Rayleigh, but the signal to noise ratio of a Rayleigh channel becomes an exponential distribution. So once we have, so taking a step back, the purpose of adopting such models is for us to understand the performance of such a communication systems operating in such a channel, right? So now that we have a distribution or a model for the signal to noise ratio, then we can try and understand, and calculate the performances, evaluate the performances of communication, wireless communications under such a channel. Right? So now that we have a model for the signal to noise ratio, which is a random process because the environment is randomly modeled or created, right? And therefore the received signal to noise ratio is also random. So if we have a probability density function or a PDF of a random process, that means that we have full information of that process. We cannot have any further information beyond that. That's theory of random processes. Right? So once we have this information for gamma, which is the signal to noise ratio, then the outage probability is defined by this probability, right? The probability that gamma falls below the gamma 0. The probability that the received signal to noise ratio falls below a prescribed value is your outage probability. So if you want to have 10 dB of signal to noise ratio to operate the link, but if your signal to noise ratio falls below your 10 dB, then that means that it's outage. Good thing for gamma, in this case, given its Rayleigh distribution, this probability can be readily solved or evaluated using this density function, because we know the probability density function of gamma, which is exponential in this case. So this probability from this density function can be then evaluated, and we have a very simple result for a Rayleigh distribution. So that's how the result is very straightforward or simple to understand or to use, I suppose. However, you need to understand and backtrack all the way to line of sight, non-line of sight, Rayleigh channel, etc., how this result came by. Okay, so that's very important to understand. And in the question that we're going to address, we're just going to use this result because it's given that it's a Rayleigh channel. So we know the outage probability of a Rayleigh channel is given by this. And we're just going to plug in values and find results. But in reality, now this is the worst case scenario of a non-line of sight situation. It cannot get any worse than this, theoretically. In practice, however, you can come up with a practical or an empirical distribution for gamma, right? For that region, for that environment, whether it's indoor, outdoor, metropolitan, etc. And then you can then go with an outage probability estimation or calculation for that region. That's how practically it's done, right? In this case, we can readily resolve because it's we have a theoretical model. Okay, so let's attend to this problem. So please feel free to ask questions, right? As I mentioned, this is the best time for you all to ask questions. So week 4, question number 1. So we have a Rayleigh fading channel. With the gamma bar, which is the mean signal to noise ratio received, 20 dB. So if you look at the probability density function of a Rayleigh fading channel, which is 1 on gamma bar, exponential minus gamma on gamma bar, right? This is the exponential distribution of signal to noise ratio in a Rayleigh fading channel. So the entire distribution is just characterized by the mean value. So once you have the mean value of a Rayleigh fading channel, that completely characterizes the distribution for the signal to noise ratio. Right? So as long as you have the mean SNR, we have the full information. So part A, gamma 0 requirement is 10 dB. Okay. Gamma 0 requirement is 10 dB. And the outage probability given by 1 minus exponential minus gamma 0 on gamma bar. So this is the result that we obtained for a Rayleigh fading channel, which is from the exponential distribution for the signal to noise ratio. So here we know what gamma 0 is, which is that, and gamma bar is something given to us, 20 dB, we just need to substitute values. Exponential. So this is not in dB, so this model is not in dB, so that's in linear scale, right? So you've got to be careful in substituting. In adopting a model, you need to understand whether it's a model that it's in dB scale or linear scale, right? So the long distance path loss model is in dB. The log distance path loss model, right? And log normal shadowing. So this one is in linear scale. So you've got to convert them to dB. So gamma 0 is minus 10 dB, which is minus 10 in linear scale. And then your gamma bar is 20 dB, so that's the 100. Right? So 10 to the power of 20 by 10 is 10 to the power of 2, which is 100. So that's 20 dB and that's 10 dB. And then when you compute this, you should get around 0.0952. Okay. Any questions? And then likewise part B, we have T0 is 1 minus exponential minus gamma 0 on gamma bar. That's 1 minus exponential. Your gamma 0 is gamma 0 in part B is 20 dB, right? So your threshold is 20 dB, so that's minus 100, 20 dB divided by minus 100. So which gives a P0 of 0.6321. Alright. And then part C, I'm just going to write the answer and then you can do the calculation, is 0.9813 for a gamma 0 of 26 dB. Okay. So in these problems, part A, B, and C, the channel is the same, the environment is the same. Why? Because our gamma bar didn't change, right? So gamma bar is 20 dB. So it's the same environment, same system, but our requirements are changing. Our gamma zeros are changing from 10 dB to 20 dB to 26 dB, right? So you can see the corresponding outage probabilities that you will be achieving. In a 10 dB environment, in a 10 dB Rayleigh fading environment, expecting a 26 dB of threshold, you're going to be outaged 98%. That means that you almost don't have a leak. 98% of the time, you won't have a leak. Right? So that's how you understand this system design. So in a 20 dB channel, mean 20 dB channel environment, expecting a 10 dB, has got 9.5% of outage. Still really high. In telecommunication systems, the expected outage probability is around 99.9. Sorry, 0.0. Availability is 99.9. So even that will have a lot of customers unsatisfied, because 99.9 leaves a lot of customers. If you take the probability, if you have like 1 million customers, we take the ratio of that, there will be still thousands of customers. That's not good enough. So you got to usually go with 99.99 or even 999. And systems like wired systems, optical systems, fiber to the node, where you can really characterize the issues compared to a mobile system or a satellite system, the expected availability. So the availability is the complement of outage, right? So expected availability should be around 99.99. And for satellite and mobile systems, usually it's 99 point something or 98 something. If it gets to 98, there's something wrong. So fundamentally, so it needs to be addressed. Okay, so that's how systems are modeled. Okay, so as I mentioned, the problem that we've solved is pretty straightforward, because we adapted a model and then solved the problem. But you need to understand the context. Right? Any questions? So we have a second part to that question. So this is Q1, 1, and then we have a Q1, 2. Okay, so why don't you guys just give a try of second part. Which says, so what should be the received signal to noise ratio to have an outage of, well, not more than 0.02. So your outage is 0.02. In the same environment, what would be the signal to noise ratio? I'll give a couple of minutes on that. What should be the received SNR to have an outage of 0.02? Should be a direct application similar to the first part, but just want to give a couple of minutes for you all to try that out, so that you're familiar with those expressions and equations. Let me know if you have an answer. get me an answer in dB, right?
Yeah, maybe. Probably the other one. I don't know. I thought the other way around because you see, it's wait a second. As long as I equal to this one. Oh, right. Okay.
Right, I'm going to give another minute. I just want to make sure you all try this out because it is a straightforward problem, but I just want to make sure that you can solve it by yourself. This is a tricky part, isn't it? Sometimes the problem seems to be really straightforward when I solve it, and when you try to solve it, you know, a lot of things goes through your mind.
This one is not. This one will change to linear.
Yep.
And then this one will be enter linear.
Yes.
That will you lock 10 of linear. And then this one.
Yeah. Yeah, gotta put a 10 in front. Gotta put a 10.
10,
Yeah.
So how many of you all did get an answer of 3 dB or 2? Appreciate it. You can just raise your hand. Just 3 dB or 2. All right. So for small percentage. So let's do it. The screen.
So this is this one. Change from linear. So linear. This one.
So the question is, what should be the received signal to noise ratio for an outage of 0.02? 1 minus exponential minus gamma 0 on gamma bar minus exponential minus gamma 0 is what you're trying to compute, and gamma bar is 100. Then you work around, rearrange the terms, you will probably get the gamma 0 of so this, just use this equation here. 1 minus T0 of log minus 1 on minus gamma bar. So gamma 0 equals minus that. And when you substitute values here, so that will be minus log 1 minus 0.02. Gamma bar is 20 dB, which is 100. And that will give you the value of 2, which is 3 dB. Right? Okay, so any questions with that?
This is the one.
All right, so let's move on to the next question. So we have a linked budget question now. So previously we had used linked budget to design systems. Transmitter, receiver at a distance, path loss, mean path loss, how do we calculate receive signal strength, etc. and so on, right? This path loss example. So now our linked budget problem or system design problem is also going to include shadowing, shadow fading. So now we're going to introduce the outage KPI of the system, outage of the system into the linked budget equation so that we can design the system with the KPI of outage for the link for the system. So in other words, we have a transmitter and receiver in an environment, shadowing environment, and with a particular requirement, how do we model it? Okay. So consider the following wireless transmission system parameter in the downlink from the base station to the mobile unit. Receive transmit antenna gain, transmit power, path loss exponent alpha equals 3.2. So once you know the path loss exponent, then we will say we know that it's going to be the log distance path loss model. So the log distance path loss model is the mean path loss, right? Doesn't involve any shadowing or small scale fading. So mean path loss calculated through the path loss exponent. Path loss at reference distance is of 10 meters is 43 dB. So here frequency is not given, and you don't need the frequency because you don't need to calculate free space path loss because the reference path loss at reference distance is given directly 10 meters, which is 43 dB. Receiver noise power is minus 90 dB. Determine the distance of the mobile unit from the access point that would achieve an outage probability of 0.1 or below in a Rayleigh fading environment for receiving a gamma 0 of 10 dB. So this is pretty much linking that problem with link budget or link design. So it's clearly understood. So let's try and solve this. Question 2. So we have a base station and a mobile device. This is the distance that we don't know. Receive antenna gain is 10 dB, right? Transmit antenna gain is 5 dB, right? transmit power is 17 dBm. Alpha, the path loss exponent is 3.2. Path loss at reference distance D0 equals 10 is 43 dB. Right, so that's the path loss at the reference distance of 10 meters is 43 dB. Received noise power Pn here is minus 90 dBm. And it's given that this is a Rayleigh fading channel. And we require the gamma 0 of 10 dB. And the expected outage probability should not be greater than 0.1, which is still not good, but that's the expectation for the system, right? So this is your system, and the question is, what is the distance or the maximum distance between the transmitter and receiver that would achieve an outage probability of not greater than 0.1. So we know that when the distance increases, the path loss increases, mean path loss increases, and therefore our received signal strength reduces. Therefore, our received signal to noise ratio reduces. So when our received signal to noise ratio reduces, the outage probability creeps up. So in order to achieve this outage probability, what is the distance, maximum distance that the transmitter and receiver can be separated by? Okay. So once we have this system defined, we can use Wien-Quadrant equations to solve the problem. So let's calculate the mean received signal strength in this case, right? So our gamma bar, so outage is given by 1 minus exponential minus gamma 0 gamma bar, and we know gamma 0, that's the expected value, T0 is expected value, so gamma bar is what we need to calculate, which is minus gamma 0 on log of 1 minus P0, just rearranging these terms, right? So when we substitute for gamma 0, we will have minus 10 on log of 0.9. That should give us 94.9 or equivalently 19.8 dB. So this is the gamma bar value, right? Then gamma bar is the expected received signal to noise ratio, which is P R minus Pn, because signal to noise ratio is signal strength on noise strength, or in dB scale, it's signal power minus noise power, right? And therefore, our received power is gamma bar plus En, right? want to calculate the received power. So gamma bar is 19.8 minus our sorry, yeah, plus minus of 90. Noise power is minus 90. That will give us a received power for this requirement of minus 70.2 dBm. Right, so the objective is to use the path loss exponent equation, path loss, long distance path loss model to calculate the distance or the separation between transmitter and receiver. So once we know how much path loss can be accommodated to achieve this, then from that path loss, we can use the path loss model to calculate the distance. So that's the objective, right? So I'll say that again. So we need to we need to determine the distance of the separation between transmitter and receiver, and that means that we need to calculate the path loss, right? Determine the distance of the separation. And to calculate the path loss between the two for these requirements, we use the link budget equation. And once we calculate the received power, which is minus 70.2 dBm, then we can use the link budget equation. So as power received is EIRP plus GR received minus your path loss, that is distance D. So power received is minus 70.2. EIRP is 22 dBm, right? 17 plus 5, so it's 22 dBm. Plus your receive antenna gain is 10 dBi minus your path loss at distance. So your path loss at distance D becomes, so we just rearrange the terms, 102.2 dB. So that's your path loss. So now you calculate the path loss for these requirements on the transmitter and receiver side, and then you use the path loss model now to determine the distance, calculate the distance. So we know that path loss at distance D is equal to the path loss at distance D0 plus 10 alpha log base 10 of D on D0. This is the log distance path loss model. You know what alpha is? PLD0 is given, and therefore D0 is, and also D0 is given. And therefore you just need to find D from this equation. So I'll say that again. Alpha is given, D0 is given, PLD0 is given. So from this, we need to find D because we know what PL is, which is 102. So just write that step as well. And the path loss at reference distance is, what's that number, 43, plus 10 times alpha is 3.2 times log base 10 of D on 10. And then from that, you can calculate D around 780 meters. So from less than a kilometer or 700 meters, 0.7 kilometer, is when you will have this. Okay, so any questions on that? So the next question is related to multipath profile. Okay, so in a multipath environment between a transmitter and receiver, such a profile is known as known as the power delay profile. The received signal strength or power plotted over the corresponding delayed versions of that same signal, copies, right? It's known as a power delay profile. So by observing this power delay profile, can you tell me whether it's a line of sight or a non-line of sight channel? Anybody?
Line of sight.
Line of sight? There's only another answer, so anybody going for non-line of sight? Well, there's a third answer, which is no answers, right? So it's like the third option is what's preferred. So this is a non-line of sight scenario, right? Why? Because the first component that you receive has got less power than the subsequent, than the delayed versions.
Oh.
So if it's a line of sight scenario situation, your direct path component will be much stronger than the reflected path because it travels more distance before it gets to the receiver. Right? So here the first component, even though it has got lesser delay than the others, it has got lesser strength as well in terms of signal magnitude compared to the next component that's received. So it doesn't mean that it's just one single ray, so it can be a cluster of rays that's coming along at 2 microseconds delay. That kind of superimposes together to give a stronger signal. So if we expand this into, let's say, nanoseconds, and if we expand that, you will see a lot of components here. And then when we aggregate that over microsecond range, then that kind of adds up to a stronger component compared to here. Right? So that's how your signals that you will see. All right. So the way that we study multipath channels, that how bad is the delay profile? That is, the delayed versions and its corresponding strength. Right? So you can get delayed versions with, let's say, 10 to the minus 10 of dB compared to the original one. Is that significant for us? No, because that's pretty much noise for us. So what's the strength of the components, the delayed components, compared to the first received component? Right. So there are 2 key parameters defining this. One is the mean excess delay and the RMS delay spread. The mean excess delay is from the first component, what is the mean delay of the remaining components, right? So if the mean excess delay is, let's say in this case, 1 microsecond, most of the components are situated around 1 microsecond delay. The mean excess delay is, let's say, 10 microseconds. So these components are situated around here. A mean excess delay is basically gives you a static environment of the channel. So if nothing's moving in this room, and if you have a transmitter and receiver, and we will be having multi-part scenario, we will be having a consistent power delay profile because nothing else is moving around. If people are moving around, then the delayed versions will kind of move around like that depending on the movement, the mobility of the environment. Right? So in reality, that's the situation, right? So so when the transmitter receiver moves or the surrounding changes, we have a power delay profile that randomly moves with random fluctuations of strength. Right? So in that case, there's a second parameter that we define the power delay profile, which is the RMS delay spread, or the root mean square delay spread. How much is this moving by? The RMS root mean square, right? So if the delay spread is too much, that's not good, right? If the delay spread is close to 0, then that means that the delayed components are kind of segregated to a particular point or a particular delay. Now, if we have a static environment, then compensating for a delayed component is pretty straightforward. We use something called the channel estimation method to estimate the delay and then compensate the delay and then recover the signal accordingly. Right? So those are very well established methods and techniques. We don't cover that in this course, unfortunately, right? It's called equalization, channel equalization. However, when we have a mobile environment, it's moving around, and the delay spread is much, it's growing. Then we have a problem. Right? If it's a harsh environment, a very high mobility, then the delay spread will be severe. So that's how you understand multi-path environments. Okay. So in this problem, given this power delay profile, mean power delay profile for a wireless channel, we need to calculate the mean excess delay, the RMS delay spread, and subsequently the others as well. Right? So let's stop there, and then we will continue the discussion and the solution in the next class. Not next week, but the week after, because next week we have the assessment. Right? So please be on time, and